So first of all, thank you for hosting me here in this beautiful place. And so let's say that at this point I'm more or less a neighbor, a close neighbor to this place. So okay, I'll try to hopefully make this talk a bit interactive. So please, if you have a question, don't wait. And let's say I have a brief introduction just to give an idea of the main theme that is underneath, let's say, all my last research activities. But but mostly I will talk about two different projects where the common idea is this idea of sharing knowledge. That means that you try to take advantage of prior knowledge or some form of external knowledge for solving large-scale visual recognition tasks. And so as you see, let's say the two final tasks are quite different, but there is something in common. So, but anyway, as you know, in the last year we have seen a lot of interest in computer vision, and for sure there are many things that now work very well, especially but more or less many of the most important vision tasks usually follow try to solve questions like this. For example, I have an image, I want to know what objects are in the image, maybe what objects and where these objects are. So these are the classical image classification task or object detection, for example. And usually the paradigm that is used is a fully supervised paradigm. So let's say I have many training examples for hopefully a lot of different classes that I want to recognize in my images or videos. Then I have a fancy machine learning or pattern recognition algorithm that try to learn from the example that I can provide a statistical model that is able to characterize a particular class of objects, for example, in images. And the output, hopefully, for an image like this one is something like that. So I can say that in this image there are a car and some persons. This is an example of image classification. Obviously, I can try to do something more better, like trying also to localize. So, for example, putting bounding boxes, and this is the classical object detection task in vision. Or maybe even trying to go to directly to the pixel, so like image parsing or image segmentation, basically. But all of these tasks with also completely different kind of models, but usually use a fully supervised task. So we can say that for sure a lot of the also hype that we have today with deep learning and all these, in particular in vision, is not only, let's say, related to the algorithms or to the techniques that are used, but is for sure also related to the data sets that now are available. And the huge contribution here is the ImageNet project. So let's say the new era of deep learning started with the group of Hinton that that tried to use deep learning model that at the end is more or less the same architecture that was proposed 15 years before, with some new tricks, but more or less the architecture is the same. One big difference is, besides all the technical, the GPUs, and that is obviously has a great role in this, but there is also ImageNet that allows to have enough information to learn representation that are good for these tasks. And so we can say that, and this is something that you can observe here. So ImageNet, large-scale visual recognition challenge, for a while, let's say till 2011, in this task, this is the image classification task. The best teams were able to provide the performances like this. This is error in classification. So this means that the state-of-the-art model in 2011, and this is pre-deep learning, let's say, this is the best performance that you can obtain with a bag of words model and all these fancy usually kernel algorithms that were built on top of that. Then in 2012, this is the Nips paper that I was talking about few minutes ago. Starting from here, and so you can see a huge gap in performance. All the new models are based on different architectures. So this is, let's say, the last interesting competition where the error here is around 3%. And you can say that I worked at Stanford in the, my advisor was Fefeli, that is the one that started the ImageNet project. And for her, the ImageNet classification task was done, was not interesting anymore, let's say, in 2014. So when I moved to Stanford, for her it was already a closed problem. Because if they have done this is not exactly comparable, but there is, because you can ask, okay, this is the best algorithm now can say, can classify 1,000 of classes in million of images with a 3–4% of error. What is an error of a human?
By the way, this is the error of a single human.
This is, exactly, exactly. Okay, there is, they have an HACCP paper. Okay, these numbers are not comparable. So there is a lot of hype here, because if many people say that the best algorithm now for image classification reach superhuman classification performances, and this is not, it's not true in general. But this is based on some evidences like this one, where this is Andrei Karpathy, so this is not a standard person, because he knows very well besides it's a very smart guy, but it's also, he knows very well the images that are there. So, exactly, but anyway, his error is higher than and this is 2015. In 2016, the Microsoft paper, the ResNet architecture, gave even better results. I don't remember exactly, but it's around 0.0 to 29, I think, something like that. But anyway, the point is that this is not directly comparable, because obviously he tried to do the same experiment on a smaller scale, because it's, he didn't try to recognize 1,000 of categories, obviously, right? So it's not directly comparable. But this gives, this gives an idea of how hard is this task. I also tried this, because he did the experiment when we were office mates, and so I saw him when he tried this, and it's true. It's very boring, but it's true that for some specific task, in particular the let's say the fine-grained image recognition task, it's easier for a machine than for a human, because, for example, in ImageNet there are a lot of let's say flowers, animals. For example, there are a lot of species of dogs, for example. And in that particular scenario, an image classification algorithm that has enough information to train a model is better than us, because there are some random, some species of dogs that a normal person doesn't know what these are. And usually in that are the classes where the human fails. Yeah.
I was just going to mention that Karpathy did like just on 100 classes.
Yeah, exactly. Yeah, there was the same. Yeah, and also knows a small number of images. I don't remember how many, but like, yeah, exactly, few thousands.
That's a nice book
on this. Yeah, exactly. Yeah, exactly. So anyway, so some people say that image classifications, image recognition, more in speaking more in a more general terms, is a solved problem. I do not agree on that. I think that is a solved problem in this specific scenario, like in ImageNet, where you have object-centric images, where the content of is more or less object-centric, means that there is one it's a single class classification task usually. Even if you try to assign multiple labels, the dataset has been collected as a single label task. So it means that usually you have one class that is that dominates the others. So it's persons are usually in the center of the image. But for example, if you look at web images, like let's say Flickr images, like in Pascal VOC, that was more was harder from that point of view. There are more clutter scenarios. There are more intra-class variations. So it's it's not the world is bigger than ImageNet. And moreover, so this is, let's say, about the something about the quality of the images. But there is also another point, that is that there are very few scenarios in which you have access to millions of images that are more or less distributed in the same way for each classes. And this is the case of ImageNet, where each class has more than thousands of examples to train on. But usually the world is different. So as all these phenomena, also the if you try to scale not to thousands but to millions of really to millions of images, and also to unfrequent labels, the distributions of the images per label is something like that. It's a long tail. So you have some images where you have a lot of examples, so it's easy, like cats. You have all the cats that you want on the web. But there are a lot of concepts that there are very few examples. And even if you are Google, the problem is that, there are things that it's very hard to collect images, because people doesn't care about that too much, let's say. So the idea, this is the main motivation around a lot of work that I've done. So let's try to really focus on the large-scale scenario where you have large vocabularies of labels, and where it's on the one hand, it's hard to collect data to train on, or on the other hand, is also, as I said, it's also hard to collect examples on the particular cases. So let's see how, and this is the sharing knowledge part, let's see what can I do with examples that maybe are not known at training time, but I can try to take advantage of similar concepts at test time. And this is particularly the scenario in which this kind of observations are very common is the web scenario. So I worked a lot on this because on the one hand, on the web you have all the images that you want. And this is something that in the years grown exponentially. So now you have more images than on videos on YouTube that you can either try to use. So the point is that the data are there, but you don't have annotations. So the real problem is how to collect annotations. One interesting thing on the web is that you have a lot of external contextual information that are not as good as a human annotation, but can help to have a quick grasp on the content of the image or the video. So the first part of the talk is exactly in this scenario, and this is a paper that we have done at this point 2 years ago, more or less. Then there are some follow-up, but this is the main idea, where the idea is to try to, the task is automatic image annotation, so this is image classification. This is slightly different if you compare this to the image classification task on ImageNet, because here usually this is a multi-label task, so you want to assign multiple labels per each image. And the idea here is to try to take advantage of the image metadata network. So this is on the web scenario. So in particular, we use Flickr images. So that is how we can take advantage of the contextual information that is related to the image to have better visual recognition model. And so the main motivation is something like that. So this is an image that you can, this is a Flickr image. One example of the image that we will try to recognize. And so the first question is, can you guess what's in the image? Let's see how many different. This is not this is not an image that you can. Okay. Any other idea? Okay. Okay. So you're pretty good. So okay, you can guess maybe a petal. Someone was very specific. This is a petal of rose. These are examples. Are real. People try to try this. Like for example, someone saw a fruit here, like a strawberry, probably. If you are very if you you can also see a tentacle, maybe. But anyway, so the idea is that suppose that it's hard in this. For sure, this is not prototype of a flower image. If you look for a flower image on ImageNet, for example, or any image classification dataset, you usually don't find an image like that. But so the idea is that, okay, this is maybe hard to recognize, but you have some, this is not the only data that is associated with this image, because maybe you can have tags. You can have also additional information, such as the fact that this image belongs to groups that are like galleries of, public galleries of images. Maybe you have a GPS data attached to the image. The idea of this model that I'm going to present is that, okay, let's try to see if using this contextual information, I can find a pool of images that are probably related to the image that I want to recognize, and try to use, and then if I'm able to find this neighborhood, this context of the image, let's see if this can help the recognition process. This is the idea. So we presented this model where we have two different phases. In the first step, we have a non-parametric, this is a non-parametric step where the idea is, so I'll briefly introduce how what we have done, but basically this is based on a simple nearest neighbor approach where you find, this is based only on the metadata. So we are not looking at the pixel. So I have an image, the flower that I want to recognize. I use the metadata to find this neighborhood.
You're looking for the tags,
for the tags, for example. Yeah, exactly, for all this additional data. So then I have this neighborhood of the image that is noisy. So, but I'm okay with that. That is that these are candidates of images that are probably related to this somehow. Then there is and this step, as I was saying, is based only on the metadata. In our case, are tags, sets, groups, and all this kind of social network-based information. Then we have simple features vector on that, like indicator vector, for example, on the tags. Then we use, so this is basically a retrieval approach. We use this is a little bit not exactly like that, but this is the idea. Then we find using, for example, Jacquard similarity, so this is the set similarity on the different metadata, but we found the most probable candidates. And then in the second step, this is a parametric step, and this is a deep learning approach. So here we have, for each image, basically this is a fusion scheme. So the idea is that at this point, we only use the visual features. So these are, let's say, these are the three, for example, images that are in my neighborhood. This is the image that I want to recognize. So I have these are two fully connected layers, where there are other things, but this is the basic idea. So we have two different components, one for the image and one for the neighborhood. At each layer, I learn some hidden representation that try to merge, to blend the visual information of the image and of the context. And this is supervised, this part is supervised. So at this point, obviously, the idea is that you try to enforce similarity when you merge the images based on the ground truth labels. This is basically what I said. The point is that at the very high level, this is what you can observe. So this is an image where we are showing this stuff. So these are the weights that this is the thing that are learned by the model. So the idea is that you have at the end, at each layer you concatenate the neighborhood. So here you have only two neighboring images. Usually we use more than that. But the idea is that you have one component for the image and one component for the neighborhood. And what usually happens is something like that. Here, this is the plot, a real qualitative example where you have, for each row, you have an image in the validation set. And these dimensions are this is the size of the weights that are assigned to the last hidden state representation for the image and the neighborhood. these are the points that are relevant for each example. So what happens is that if you observe images, for example here, where you have very high values for this part of the model, this means that, so you are using mostly this part, not this part. This means that you are doing, you are not adding anything more with respect to the original features that you can extract from the image. So this is something like a standard AlexNet VGG architecture on the image. And here you can, so the images that are like this, where you have high value here, are images, for example, for the class, let's say moon, or this is a marriage, picture from a marriage. This is a city, this is zebra. So these are more or less prototypical examples of this class. If you move to the other part, if you have high values here, this means that you are using more the context than the image. More the features that are related to the context than the features that are associated to the image. And here you start to see images like that. So, for example, here you can still see that this is not there is not the bride and the groom, but there are only all the people here that are waiting for the flowers. This is again two photos from two pictures from cities, but this is not the classical skyline of a city. Or again, this is a moon, but it's hard to recognize. So these are examples that are closer to the rose pictures that I showed at the beginning. And so this is basically the idea. And one main motivation for this model is that when we start to work on this, there was these two different works that claim state-of-the-art results. On this dataset, this is the Newswire dataset, where you have this has been collected in Singapore in more or less 5-6 years ago. And this is not it's not a really large-scale dataset because you have 240,000 images. The interesting thing is that this is collected from Flickr, and you have ground truth for only 81 labels. So the evaluation here is done on these 81 labels because you can evaluate because you have the real human annotation. And at this point, the best work before ours were, let's say, a bit complementary, because the first one, and here is the idea of using networking, social network data, was this work that was presented actually in Florence in 2012. And this is from another group from Stanford, but they work from Yuri Leskovich. I don't know if anyone have heard from him. He's very good. He's one of the most famous professors in social network research. And so they at that point was good because they claimed better results. They had the state of the art here using only network metadata. So they didn't look at the pixels. Then a couple of years later, in 2014, this is the other two work. This is a work from Google, where they show better results using only, at this point, this is based on graphical models. This is based on deep learning. So here they use only a standard architecture that basically AlexNet trained on the on Flickr images. So our idea was to try to take advantage of both the, let's see what we really can do using both the information at the same time. And this is what we obtain at this point, that let's say we get significant improvements. But I think that more than the numbers, it's interesting to see some qualitative results. And so this is one of my favorite examples, because here our baseline, this visual only, is we started from pre-trained features. So the features that we use to blend the information are the output of a network that has been trained on ImageNet. So let's say that, and this is the visual only model. So this is similar to the Google paper and to any of the architecture that you can use on ImageNet. And if you try to recognize this image, to classify this image, the best classification model here that looks only at the image gave these results. So water is okay, but animal and flowers are not are wrong labels. The point is that if you look, for example, at flowers, this makes sense because there are a lot of flowers in ImageNet, and so probably you learn a lot of filters that are very good to recognize this shape where you have with very specific colors that usually is the center of the flower, right? But this is what probably happens here. In our model, we start from the same, but in this case, our neighborhood is something like that. So this is the neighborhood that we online we are able to find using the network metadata. So here, probably we are able to solve this task, especially for person, because in the neighborhood you have a lot of images that are obviously pictures from that are related to swimmers and things like that. Or again, in this other example, you have here this image. The problem in this image is that it's interesting again because you have clouds, for example, here, and here you have it's obviously something that is not related to that, but there is kind of foggy thing that is related to the guns. But here, so this is probably the thing that is misleading for the network. But again, if you use a network where, a context where you have a lot of examples that are not all a good example, like this one probably is an outlier. But again, the network is able to take advantage somehow of this to solve the problem. Or again, you have another example of that. This is a good one because, for example, here we have this is a weird image, but again, here you start to see something. There are drawbacks in our model. For example, here you have this outlier that is probably the one that is, the most important example that is used to assign the person label here. So we are again not able to solve this, but again, it's better than the original one. Failure cases, again, obviously, if you have one drawback here is that if you go to the very extreme case, and this is probably the main drawback of our model, and actually there is a paper that after our that now has better results than ours that has been presented at the last CCVPR from Greg Morris group, because we chat a lot with him. He was at Stanford when I was working on that. And so they started from our model and they tried to do something better using the first thing that you can have in mind, that is to try to take advantage of the correlation between the labels. Because even if you are multi-label, you are not using, we are not modeling, for example, the co-occurrence of the same concepts in the same image. So, for example, here, a problem that we have, like in every image classification task, if you don't try to solve this kind of structural learning problem, if you have images in your training set where for example, two concepts co-occurs frequently, it might have, it might be that you try to, you are not able to solve, you are trying, for example, to learn a model for the boy, for person, but if the boy is always in a place where you have also water, you are not able to say if you are learning actually a model for the water or for the boy, right? And so this is something that sometimes happens. For example, here water is probably because you have a lot of examples where you have kids that are close to the water. Or the other one, this is another example where this is a problem because this is again a weird image, but the problem is that here we have, let's say, a really random neighborhood. So it's probably, it was problematic at the beginning and it's still problematic also later. Again, on the numbers, the point is that even if you have, so an interesting thing to observe is that in our model, usually you have some classes. These are all the classes that are in the dataset. And here you have a comparison between, let's look before to this one. Here you have our model against the visual only baseline. So what happens is that if the red points are the one where our model works better, the ones that are under this line are the labels where we are losing performance. There are many where we are more or less the same performance of the original model, but there are a lot of them where we have significant improvements. it's very interesting to observe that the only classes where the only class where we really lose performance is this map. And the reason is that if you look at this other plot, this is the same numbers, but in this case, we are looking also at the label frequency. The problem here is that for two of these classes, you have very, very few examples, like 5, 10 examples. So the point is that here, you don't have enough information to use to share the knowledge between. So actually here, if you have, let's say, a neighborhood of 5 images, if you have only 5 images in the in your training set with this label, it's obviously hard to have enough information to do the transfer learning. One of the main thing that I think in this, the interesting aspect of this model is also that these two phases allows something like that. This is one of the main take-home message of this model, that because, since we have this initial non-parametric step, we can try to do also some crazy things, like, for example, let's say that, and this is something that is related to my main motivation at the beginning about the difficulties of having enough information for some classes. For example, on the web, this is not only a problem that it's hard to collect, but also the same concept can change over time. This is not a good example, but let's think, for example, a tag like Brexit. Brexit 5 years ago has no meaning, right? Now you have, if you look, this is not a visual example, but now it's a concept that is pretty popular, right? Or for example, band. If you look for band on images, on Google Images, probably you are looking for a rock band. If you look, or something like that, pop or something like that. If you look to the images that are annotated with the label band on ImageNet, that is based on WordNet, this is the classical band where you have all the people with the big drum. It's not the same thing. So this means that you have also concepts that may not change meaning in that case, but are not probably related to the things that probably you're interested in. So the idea is that, okay, let's see what happens if you have, for example, another problem is that if you use a fully supervised setup, another problem is that, for example, if you have a new label like Brexit, you want to train your model, you have to recollect everything and learn everything from scratch. So that is that, okay, let's see what happens if in this, for example, for the labels, in this initial stage, I use a vocabulary to train my model that is different from the one that I have at test time. What happens with our model? And we can do that because it's not, it's not a problem for the nearest neighbor non-parametric problem, because here it's not, you can also have different vocabularies with that. So the idea is that, let's see what happens. Okay, let's say this example, 100% of overlap means that you have the same vocabulary of labels at training and test time. 75% means that you have 25% of the labels that are different. Probably this is enough because it's more than the real example, because it means here you have thousands of labels, so it means 25% is a big number here. But even if you go to crazy thing like 50% of differences between training and test, 25%, then this is very good, because what happens is that this is again the same baseline that we observed previously. This is the previous state of the art, the URL scratch work. What happens is that this is mean average precision, so higher is the better. These are our best results, but even if you have vocabularies that are not, for example, 75%, you have again significant improvements. And even if you go to do crazy, you still have observed a huge number. The same thing can be done on different metadata. So this is interesting because the main message here is, let's see what can be done with information that are not, that you can trust completely, that might be there, because and this is the case of network, social network metadata, because for example, user tags can be there, can be wrong. For example, I don't know, an image where you have the tag that has been tagged with airplane is not the best example to train an airplane detector, because a lot of the images that, if you look for airplane images on Flickr, many of the first images that you see are images from the airplane depicting the outside. So it's not the thing that you want if you want to, I mean, probably it is an image, it's not that it's wrong, the label, it's that the purpose of the people that have tagged that are different from the one that you have. Or there are a lot of images that are from people inside, I don't know, like your kid that is in the airplane. Yeah.
0% overlap.
Yeah, you have completely different labels. What happens here is here you take advantage of the concurrence that I was saying. And yeah, that is, yeah, no, in fact, I mean, we didn't expect to have, I mean, we thought that it probably is, this is really related to that. I mean, so you have to do this, and this is random. I mean, you have like, the vocabulary here is like, I don't remember exactly, like 6,000, 7,000 labels. You split randomly. So it's probably, if, I mean,
would it look like that the concurrence was much more than having the label with respect to the visual only?
Yeah, this.
The concurrence is the one that is the difference between the visual only and visual.
This is okay. This is just to build the neighborhood, right? You still have your original image, and this is right, because that part is fully. Okay. The point is that even if you add random images, the network, the second part of the model is able almost always to understand if the network can trust the neighborhood or not. So if you have completely random thing, usually you don't use that. So the network at the end is like having the only visual model. Okay. But if you have a sufficient amount of information that is more or less okay, you are able to take advantage. If you have good, I mean, if this is the main point. And you can do the same even with different modalities. For example, you train the model with a neighborhood that has been built on tags, and at test time you use another things like groups, GPS or we don't use GPS because we didn't have enough images that with the GPS data, but we tried also that. So obviously it's not always the same, but here the baseline is 45. So all these numbers are 3 up to 8 points in average precision. On this data set is a lot. So this is the first part. So here the idea was, let's see what in this first part the work was, okay, let's see the context. So the knowledge that we use, that we try to share, is built on top of this social network, metadata. In this second work, this is with Silvio Savarese, and here the task is completely different because the idea. Yeah. No, he's completely, no, here, this is a fun thing, because here the point is this one, that this student, this was a visiting student from Francesco Palmieri in Napoli, and because he started to work more on vision things, let's say, more on the, because he is, he did neural network, yeah, exactly. But, yeah, so that was, I'm still collaborating with them because with another student from his group, but this started because there was this visiting student there, so he started to work with me on this task. So at the end we got this paper to the CCV, so we were very happy because it was not easy. But the idea, so we start to work on this task where the idea is, and this relates to a lot of things that I'm doing now. So the idea is to try to move to not more, here we are not talking anymore of recognition, but more on the, let's say, predictive vision. So we have a lot of works on this idea of trying to take advantage of the visual knowledge that you can extract from an image to try to predict what is going to happen in the near future. In this case, in particular, the idea is to try to learn motion, specific features, to do motion prediction, where the idea is, this is trajectory prediction. So actually, we don't have real pixels here because the input are the coordinates of points. So this is a time series prediction. And the main motivation is that we started at Stanford, this is one of the projects that there are multiple projects on the same, let's say, tasks. where the idea is to try to predict human behaviors at a large scale in different contexts, but the idea is to try to scale in terms of classes and also of, because I mean, mostly they say about classes and number of different scenarios. And so to this end, we collected these data sets at Stanford, and this was a huge, huge, huge work. Because we have, so the idea here is to, and we make this data set public, where there are different projects on that, but all of them try to, the task usually is human behavior understanding. And in our case is also not only understanding, but also prediction. So trajectory prediction of, for example, pedestrians, bicycles, cars, or things like that. And from an, let's say, the application side of the thing, you can see it's obviously interesting to, in context like, for example, autonomous driving. So for example, if I have, I can recognize a pedestrian, I'm really interested if I have a model that is able to predict what the pedestrian is going to do in the next 1, 2, 3, 4 seconds, something like that. And so for that, to do that, we collected this data set from a drone, so on the Stanford campus. So we have these Stanford drone data sets that where you have like 20 different physical spots in the campus, where we have ground truth annotations for, I don't remember the exact number, like 10 classes, but actually you have 3, 4 that where you have really a lot of data that are pedestrians and bicycles, the two that we use in our work, only bicycles and pedestrians. And here the ground truth means the trajectory. So you have, for each point, you have the exact trajectory for each one of the people that you can observe here. So this was really painful, as you can imagine. And obviously, I mean, there is a company that did that, some of this work. But this is an interesting data set. Now, I mean, we started, this project was led by another postdoc and me for the knowledge transfer part, let's say. But this was a huge, I mean, actually this work we tried for CVPR 2016, and it didn't work because the dataset collection was definitely harder than expected, so we didn't have experiment in time. But anyway, so the idea then is to, when I say motion trajectory prediction, this is the idea that, let's say, a person, usually given, even if you give a single picture to a person or in a new place, for example, this is probably the worst place to make this example, because usually the other time I say something like that. If you look outside this building, you have cars and all this, but this is not the case. But anyway, so this doesn't work here. Yeah, exactly. Probably here it doesn't work. This thing doesn't work. This is interesting. I didn't follow it. But anyway, so that is that if you have a new scene, even if you look at a scene that is new for you, you are more or less, you have an idea of what is going on there, and maybe also you can try to predict the most likely behavior of the other agent, like people or cars that are in the same scenario. And the claim of our work is that this ability is mostly driven by two main factors. The first one is the fact that human has a lot of prior knowledge about the dynamics of previously observed agents. Like, for example, like here, like bicycles, right? So you know that, for example, usually bicycles or car moves on the road, not on the sidewalk or on the grass, let's say. So one is the dynamic, so the trajectories that you have observed in your life. Then you have the semantic of the scene. So as I was saying, you know that if you are able to recognize that this is, you have a sidewalk, you have a building, you have, I don't know, like trees. There are things that can be done there, and things that can't be done there. So the idea, let's try to use here, so the knowledge that I'm talking about here, that I want to share, is this prior knowledge about the dynamics, and also this that is connected somehow to the semantic of the scene. And so this is one of the main points of the model. So the idea is that, okay, at training time, we try to learn some statistics that are related to how people or a generic agent, like a car, for example, navigate a particular scenario. And so our model is based on this representation where you have this navigation map so this is class dependent because obviously the same space is different agents, like different classes, a person or a car, navigates in a different way the same space. So we collect statistics about these behaviors at training time, and at the end, and we encode this knowledge in three main representations that we call navigation. And so these statistics are called navigation map in our model. And so we have the first one that is like it's called popularity map, where the idea is that for each patch of the image, we try to collect statistics about how popular is that particular patch for a particular class. So this means that most of this is for the bicycles, this example. So this means that usually bicycles moves here in these areas. These are the roads, right? Then we have a second term where we try to find the points, and this is called routing map, where it's more likely that this agent change behavior. So for example, for a car or for a bicycle, where you are in front of let's say a roundabout of an intersection. And then we have other features. This is totally uncrafted, not deep learning here. So here we have features like basically histogram of gradients, but here these histogram of gradients are collected on the trajectory. So this is not on the pixels. So this means that this is discretized on some directions, mean directions. So the idea is that here we collect on this particular patch, you have some directions that are most common with a particular velocity. So here we are collecting both the directions and also the velocity that are more common on that area. These are a lot. You have a lot of parameters. So on this, yeah, these are things that are tuned to the. It's very similar. I mean, actually, it's really like a histogram of gradients. So like SIFT or OG or whatever.
No, but I think that you generate another thinking on this for all of these maps.
Yeah. This is I didn't say that, but the starting point is the scene. You have your physical scene. Then we overlay a grid. Is it? Yeah. I mean, it's yeah. You have these are video. You start from video, so it's the top view of the. But yeah, this is an example for this particular scene. You have multiple of scene, but yeah, that is the. So you have a grid, and you overlay a grid here, and for each patch, and so this is the first parameter that you have. That obviously influence a lot but this is more I mean, actually here it's the resolution. You have to find a resolution that is reasonable for the information that you want to collect.
And for the second map, when you find the abruption of the movement of the trajectory.
Here this one you mean?
Yeah.
Actually, here the thing that we are doing is that you have the trajectories, let's say at training time, you find the trajectories where locally you have the change a lot. So it's like where you have a high value on the derivatives here.
Okay.
And this is again a qualitative example for two classes. So it's the same. This is the computer science department at Stanford. So, and I mean actually these are the information that we have collected for pedestrians. These are for cyclists. So for the bicycles. So as you can see, the pattern is slightly different. In particular, this one. Because here, actually, you would expect that here you have also something like that, because these are bicycles. But the point is that this is the main entrance of the computer science department. So here, usually people stop here, because you have all the bike racks. So this is very nice. And also here, this is interesting, because you can, I mean, if you know you have a real knowledge of the scene, you can, I mean, it's reasonable, because for example, here, you have a big spot here, because all the people stop here, because here is the point where you stop with the bike. So yeah, so there is change a lot. So making the thing short, so our model there, so we have two, let's say again, two components. The first one is the real model, the trajectory prediction model. And so here, and this is a simple dynamic Bayesian network where the idea is that, so in the simplest case, if you don't have any information about, so here the information, so this is a time series of position in the space, and the thing that you are collecting are the x and y position, and then we have all the information about the velocity in this particular point. So you have a sequence of points, so this is your trajectory, and our task is, at test time, is that given a point, a starting point, I want to predict what is going to happen in the next time frame of 2, 3, 5, 10 points, let's say. The work that we use as, let's say the first work for this task, the most important one, most famous one, is activity forecasting from CMU. That was the first work to try to solve this. And they proposed a model that was based on inverse optimal control. So there are some things that you'll see in the after, also in the experiment, that are related to that. And in particular, in their scenario, since it's an inverse optimal control problem, they usually record all the results in this particular setting that we will see in the experiments, where actually you have 2 points. You have the starting point and the final point, your destination, that are known. So the thing that you want to optimize is, given the starting point and your destination, what is the most probable path to go from here to there. You can remove this because obviously this is more interesting. You don't know where we are going. You can try to estimate also the most probable position, and then to learn your plan. Because usually this is used a lot. This kind of models are used a lot in the robotic community, and in particular, there the inverse optimal control problem means that you know your destination, then you optimize all your path given the final destination. And so this is okay. I already said. The main point is that if you don't use any information, any knowledge about the scene, that in our case is collected in this M, in this our navigation map, our model is a Kalman filter. It's like a Kalman filter with a constant velocity model. So it's a very simple model where if you don't use any information about the scene, usually you go straight on. You don't have any information to change your behavior. The point is that at each point, our prediction is influenced by the knowledge that is encoded in the map. So in terms of popularity, routing maps, and all the other stuff. So this is the model. The second part, so the other contribution, is to see what happens. So this is the story, let's say. The point is that to do this kind of work is very hard because, again, you need a lot of data to have a reliable, reasonable model. And actually, the activity forecasting model, for this reason, from CMU, was tested on very few examples, like in a very toy example scenario, like one scene, actually 2 different scenes, with very few examples. It's like one is a parking lot where you have a sidewalk, few cars, and pedestrians. So one of the main goals, especially on the data collection part, was to try to have a more realistic scenario to do this study. But we collected these data sets, but collecting this data is very, very hard. So it's not like collecting ImageNet, because to try to annotate even 1 minute of video it doesn't scale. In 10 minutes of videos, it costs a lot, because you have, especially if you try, this is a campus, university campus, so you have easily hundreds of people moving in the scene, so you want to collect the annotation of each second where the people are. So it's very hard. So that is that. Let's see what happens if I collect this training data only on a subset, and maybe then at test time I try to use this knowledge, that in our case means all these navigation patterns, and try to transfer this knowledge to a new scene that I didn't observe at training time. And so this is the knowledge transfer part. Here we use the idea, the main assumption is that to do this knowledge transfer part, we take advantage of the semantic of the scene. So that is that if you have scenes that locally are similar, probably also the dynamics that you can observe there are similar, let's say.
The semantic has been done by hand or?
We tried both. We started with the ground truth, then we use an image parsing algorithm to extract the semantic. So we have our image, we extract, so this is a segmentation task. So as you can see here is noisy, it's slightly noisy, especially on the boundaries. And so here we have multiple classes, not many, like these are not all the classes, but it's like 10 classes, and are like road, building, grass, sidewalk, and all these kind of things. That is then we have some context encoders, so the contextual description of the scene, where for each patch we assign, this is based on the shape context idea, so that is that we have two components, one where to encode the local patterns of the scene, the other one that look also in broader terms, and then we merge the two, and that is that, so here you have histograms that encode the percentage of pixels that have been classified with one particular label. So for example, here it means that you have a lot of road and grass, let's say. Then the same here, and you weight differently things that are close to you and things that are far away. That is then one patch, so is somehow encodes the topology of this of the semantic. Then again, like in the previous case, in the first model, we have a nearest neighbor based retrieval approach where we have in our training set patches that are probably represented by similar local patterns. The idea so then is to transfer the navigation pattern associated to this patch in a new scene. And then we try to do the prediction using this data. We have done experiment with these two datasets. This one dataset is one of the older ones where you have this video surveillance domain scenario where you have in particular 2 scenes and 6 videos. In our case, as you can see, we have definitely larger numbers. So we have 21 videos that with corresponding to 15 physical scenes, different scenes, and we use 2 classes. The thing is then here, so what we are doing here is to try to predict a trajectory in the future, and when we looked at the real trajectory and we compute the difference. Usually this is done, the standard metric that is used is this modified Hausdorff distance. This is like the mean square error, but this is slightly better than the Euclidean distance, for example. But that is that you have all the point of the ground truth trajectory and you look at the differences. So it's an error metric. And these are the results that we have. And so this is our model on the 2 datasets. This is the previous state of the art, so the activity forecasting model by CMU. This is a very stupid baseline. This is linear prediction. So this means you have your starting point. It's like Kalman in prediction. And these are other 2 models, but this is another model. But by the way, the most important is that this is our model if we don't look at the scene. And this is what we obtain using our model.
So here you are trying to predict a single trajectory.
Yeah.
You're not trying to predict all the trajectories in parallel. Taking advantage of the trajectory. We have the trajectory of person number 1. We want to predict that this is influenced also by the trajectory of person number 2. So there might be a kind of cooperation competition. We are not doing this.
We are not doing this, but I have a follow-up on this. No, actually, there is a work. No, I'm not on that. But this other colleague, that is Alexander Alai, that maybe some of you know, and he had a paper based on that is called social LSTM, and they did exactly this. So they looked at so in that case, the model that they use is an LSTM, so a recurrent neural network. And in that case, the prediction is exactly the same task. The main contribution in that work is that, exactly as you were suggesting, they use the position of the other neighbors in the sum of them, the closest one, to influence at each step your behavior, the prediction of your next step.
Okay, so it's a collective.
Yeah, I mean it's a single. The training is a single, but you look at the others. In our case, we are in fact in let's say this work is in this work we are trying to encode the human space interactions. That in our case is this knowledge about the scene, but we don't look at the others. So, for example, if I have someone that is crossing the road, I'm not able to. I mean, I don't take advantage of that to change dynamic of my behavior.
Is it possible to incorporate this information?
Yeah, we are trying. Yeah, the follow-up. The thing we are trying to do is to have a joint model. Yeah, yeah, for sure. No, yeah, no, this is an interesting. No, this. I mean, actually, I have. It's not this work, but because it's slightly different. The previous work in this area usually are really there are two clusters. One is the let's say human space interaction, so activity forecasting, this work, and another couple that try to do this. So, and usually what you are trying to do is a mid-long-term prediction. And so in this case, like in our, we only looked at the interaction between the agent, the pedestrian, for example, and the scene. The other cluster of works, like social STM, for example, in our case, they only looked at the human-human interaction. So, and is usually, and so in this case, the task that has been tackled is more a short-term prediction. So at the end, the focus is mostly on collision avoidance, because you look, so the prediction is like at 1, 2, 3 seconds, something like that. There are multiple works at Stanford. Silvio is working a lot on this, so that they have other follow-up where obviously the next step is to trying to have a model where a joint model where you use everything together. So both the human space interaction and, so for example, I briefly mentioned this.
Working together, for example.
Exactly. Yeah, exactly. One thing that I'm doing in Florence that is somehow related to this, we extended this, not this work, but the social STM one, using also, so using the knowledge about the others, as we were saying, and also of the scene. Because at Florence, they work, when I came back from Stanford, there was a couple of them that, a PhD student that was working on this big project that is more related to human behaviors, understanding. And they collected a data set in a museum in Florence, Bargello Museum. And there, the task, so the interesting part there is that, so you have, and they collected a lot of data about people, groups of people. And also, and the other interesting part is that you have also a rich semantic, because it is a museum. So the behavior of the people is highly influenced by the things that are there. Like there is the Davide Di Donatello, where there is a lot of people that are going there. So the idea, so we extended the social STM model. Here is more, yeah, exactly, yeah, that's true. But yeah, something like that. So we use this idea where we have this context-aware LSTM model where we have both human-human interaction, human space interaction that are these in this scenario.
Actually, there is a work in predicting the trajectories that are affected by people that teaches layering.
Yeah, I was, yeah. I thought of your work on game, on game theory. This is by Kitani, that is the same guy of activity forecasting.
I reviewed the paper many times.
Yeah.
What is the name of the author?
Kitani.
The main author is Kitani, but the main author, the professor is Kitani. Yeah.
Now, set of other authors in that paper.
Yeah. Yeah, but anyway, so the thing that, as I was saying, so in this work, what we are doing is something like that. So we have the starting point, then this is a qualitative examples of what happens with the blue is the ground truth. This is a linear constant velocity model, so our stupid baseline. Then this is Kitani, the activity forecasting model, and this is ours. So, and this is the final destination. So in this setting, we know that the final position is here. That you would expect is something like that. So this is an easy example, so we're more or less, this is not working, but the other one are more or less okay. The most interesting one is this one and this one, because both models use human space interaction. So for example, in both our case and also in Kitani's one, the model learn to, for example, that people usually walk in the sidewalk, not on the grass. And they take advantage of this knowledge to make the prediction. So for example, here, the yellow one is Kitani, and in both cases, more or less, you always walk on the right places, and you're going in the good direction. The point is that, especially in both, here is more or less the same, but here you have completely different paths. And the point is that this is one of the main points when we claim our work is that in our case, since we are data-driven, because we are learning the patterns at training, the behavior, how people navigate the scene at training time, we have more realistic behavior, while they usually have a big, the final destination is a big influence in the model. So usually the model tries to go to the final point in a reasonable way as fast as the model can.
It's kind of a constraint shortest path problem.
Yeah. Exactly. Yeah. This is an optimization so that they optimize the path to the destination as fast as possible. And these are numbers. So anyway, we have significant improvement over the work. But probably the most interesting is what happens when you try to do the same in a new scene. So this is what happens here, where we have the knowledge transfer part. This is just a qualitative example to see that we are trying to transfer reasonable things. So this is the at test time, the scene that where we are trying to make the prediction. This is what happens if, and so this is the numbers that what happens with the model that I've presented. Here is the same thing where the prediction is driven using the knowledge that has been transferred from different scenes where you have training data. If you transfer the patches, what you can observe is something like that. So this is like an hallucinated scene of where each patch is an average of the, I don't remember the exact number, like 5 or 10 closer points in your training set using the contextual descriptor that I briefly mentioned before. So as you can see, where you have you would expect to have a road patch, you have a road patch. Here is something that you can see that the pattern is more or less correct. Obviously, this is the part, but you don't transfer. What you are transferring really is something like that. So these are the navigation patterns. They might be super noisy, like here. You cannot, this is not the best example, obviously. The main point here is to see that even if you have very noisy navigation patterns, you are still able to make reasonable prediction, because this is the prediction that you have in the traditional setting, and this is more or less the same prediction in this context. And this is just to give you an idea of what we are really predicting. So this is at the end, we are predicting one trajectory, because this is the setting where the other works have been conducted. But actually what we are doing is to estimate probability over the space. So actually we are plotting and using the most probable path, but we are actually predicting, we have a navigation map that is more general, let's say. So for example, here, this is the model picked this particular path, but as you can see, you have multiple, two more likely scenarios, right? So probably it's more from the application point of view, it's probably more useful to have the prediction of the full map, because it means that you have more knowledge about the thing.
Why not updating this map online when you are wireless?
Because we start, this is something that exactly. No, it's true. We are one of the follow-up that where we are working on is this one. We started with this idea of, because we have also this let's say, underlying assumption that it would be super cool if you have you can do this also on a static scenario. So you have a feature, so I can predict whatever is going on, but it's very stupid to do not update, and so it's something that we didn't do that. Frame by frame, you can at least adjust, because obviously the prediction here, if you update the model, it's more likely. I mean, then you have higher confidence, and I mean, you're predicting that. So it's something that this is something we're doing with, again, with Francesco, with the other student, Francesco Falmieri, because we are working on this model. So this is one of the main criticisms that we had also from the reviewers. maybe you were one of them. Okay. Okay. But anyway, the reviewer got in, so it's okay. You were. This is another example, and okay. So just other two things. So ongoing future work. The first one is, so these are the projects that I'm working on these days. The first one is related, let's say, to the first part of the talk. So this is something that I started with Silvio, then things changed a little bit, and at the end we have this work that, this is another work that maybe is going to be accepted soon, and with Federico Tombari. I don't know if you know him. This starts super randomly, because I was working on this web supervised work, so we met at ICCD where I presented the first work. So he had a student working on, he didn't work on this task before. So we started to do this work, where the idea is to transfer, to start in this web context, starting from images. We try to learn a CNN model for activity, large-scale activity prediction. And here the idea is then is to use, so zero ground truth. We start from Google, so we download, let's say, for example, I have a class like assembling furniture. I will download images about this specific concept from the web. So this is noisy. We have one component, a random walk model that removes some of the noisiness that the noise example that you find. Then we train a CNN, and then we have an iterative process that, through time, start with a stupid model. You have the video, so with the examples that starting from the image, you learn a video model starting only from the image. You are able to recognize the class on the video, so you augment your training set, and you iteratively try to have a better model. So this is one first line of work. Then I have two works, and this is the first one is the second one is the one that I was mentioning. So this is the context-aware trajectory prediction in crowded spaces, where the idea is to use both human space, that is this component, and human space, and also human-human. So here we look also at the other in this particular domain. And this is another work, again, based on, this is another deep learning model, where here, so these are two works that we just submitted to BMVC, and here the goal is to, this is a slightly new task, we claim at least, where the idea is to predict action progress. We call the action completion, we changed the name, because at the beginning we called this action completion, we changed this in action progress. So that is that this is action, spatio-temporal action localization. So you have a video, you want to recognize the boundaries of an action. What you are trying to do is also to understand at each point in time what is the percentage of the action that you have observed so far. So, if you have the ground truth, what you would expect is a line between 0 and 1, where you have the starting point and the final point. The idea is, so this is the regression problem. So online we learn not only the action class, but also the percentage of the action. So as you can see here, this is a good example. So the green one is the ground truth. This is our action progress. So you assign also a number that is like, we are at this point, this is a guy that is jumping, and this is the 30% of the action. We think that this is interesting, for example, in an interactive scenario where you want to, where you have, for example, interactive agents. So knowing what the other is going to do and when he's going to finish the action that he's doing is something that might be interesting. And finally, this is the last one that I don't know if, I mean, if at some point we make these things work, But this is a work that we started with Fei and a visiting student in her group, where we are trying to do at the same time, this starts from the image captioning line of work, and in particular here we are doing language text grounding. So that is that in particular in this, again, in the wild. So for example, we collected this dataset from the web, where the idea is you have the image from Reuters actually. So you have a very good high-level description of the image, and we try to learn a model that is able to understand the image and to assign, to ground the phrases on the image. But let's see how it goes here.
So you use the phrase as classifier.
Yeah, it's a multimodal model, but yeah. The main, there is a huge project in Fei's group that is the Visual Genome project, where that is exactly on this, or for example, Coco from Microsoft. There are many works there where the idea is to try to make a good link between the language part and the visual part. What we are trying to do here is to have, and this is the reason why we collected these data sets, is to have something that is more at a higher semantic, also not directly. So this is here, these phrases, so these sentences are written by journalists. So it might be something that is not directly observable, but maybe you can infer from the visual part. So it's, let's say, somehow more high level. So that was the challenge, the main challenge that you can have in the other. So that's all.
Okay, thank you very much.
Okay.